Very good. Registration started. So the Stokes formula gives the velocity of sedimentation, which is a necessary element to design the sand trap. And the independent variables, I say again, in the Stokes formula are the dynamic viscosity of water mu. The more viscous the fluid is, the more is the value, the higher is the value of the viscosity. And then other independent variables in the Stokes formula are the specific weight of sediment, the specific weight of water, and the sediment size D. Sediment size is driven by downstream requirements related to water use. For instance, if water is used to produce hydropower, then there is a limiting sediment size, which is given by the manufacturer of the turbine that you use to make the power. Okay, so this is the Stokes formula, and I go back to the page, which, as I said, if you make an effort to remember at least the independent variables, would be this would be great, and you don't need to be able at the exam to reproduce the proof. Okay, and then I said that once that you know the velocity of sedimentation, I made a sketch, and we proved that it's necessary that each particle of sediment stays in the sand trap a time long enough to allow sedimentation, to allow a particle that is placed at the top level of the sand trap to reach the bottom of the sand trap itself. So this time is derived by dividing the depth of the sediment of the sand trap by the velocity of sedimentation. Okay, and just let me take the graphic blackboard. 1 second. 1 second, I need to share the right screen. Here we are, and let me, okay. So I just want to repeat the sketch because I want to be clear. We don't have to hurry up. So if I have this sediment trap, let's suppose that it's done like this. This is the sediment trap. You remember that the sediment trap is separated by steps. This is the gravel trap. Okay, and this is the sand trap. Sand sediment, sorry. Sometimes I use the two terms as synonyms, but this is the sand trap. And let's suppose that we have a water flow here. Okay, and water flows in this direction. And if you see from the top, of course, what you have is something like this. So we have the gravel trap here, and just let me put it the same. So we have the gravel trap here. This is view from the top. Okay, and here there is the gravel trap. And here we have the sand trap into channels like it is reported in the sketch in the web pages. This is the sand trap. Okay, so I have the flow that is coming from here again. And so I said that let's suppose that we have a particle of sediment here, and the trajectory and the length of the sand trap should be enough to allow the particle to settle down. Here, this is the trajectory. And so if you indicate with the symbol LD the length of the centrap here, this is LD, and there is a time of sedimentation T required to the particle to reach the ground, which is given simply by the depth. The depth, let me see if I indicated it with one specific symbol. I need to have a look at the web pages. Give me 1 second. Yeah, H. So the depth is H. H, so time is equal to H divided by WS, okay? And then at this stage, we need to know the velocity of the flow V. This is the velocity of the flow V. And once that you know V, then you can write the length of the centrap is equal to V times T, okay? And what is V? V is derived by dividing the flow, the design flow of the centrap, the design flow, the design water withdrawal. So V can be derived by dividing the design flow time by the area, let's call it AD, and AD is equal to it's the transversal area of the centrap, so it's equal to H times, let me give a symbol to the width, so this is width 1 and this is width 2, and then this is the area, transversal area or cross-sectional area of the centrap. So what we need to do is first assume a value which is given by environmental constraints for W. So what you have to do is to start with, let me take a color that is different. Okay, this is fine. To start with a gas value. This was a plus, sorry, not a times. Okay, it was W1 plus W2. So you have to guess a value for the overall width of the centrap, and this is given by the room that you have available in the sides of the river. So if you have a large room, then you can increase your width. If it's the river, it's very constrained by the slopes, then you have to limit the width because you don't want to excavate at the foot of the slopes. So you guess W1 and W2, and what are usual values? Of course, it may be, it is variable, and it may range from something like 3 meters to something like even 15 meters if you have important withdrawals with a lot of room in the sides. So you guess W1 and W2, and then you guess also the depth of the centrap. This is not difficult to guess because I said that the depth should be limited. Because of course, if you make a centrap that is very deep, it takes more time to the particle to settle down, to reach the ground. And therefore, a usual depth, which also should not be exceeded in order not to create risky situations for people if one falls into the centrap, etc. So a usual depth is something between 50 centimeters or 150 centimeters, so 1.5 meters, it's the max. And then once that you guessed these two values, you get an estimate for AD, and then you go to the computation of the velocity, because you already know the design flow QP, which is assessed through the flow duration curve or other methods. Very good. And then you look at the velocity. Should be a low velocity. You don't want turbulence into the centrap for the reasons that we already discussed. And the velocity can be in the range 0.05, 0.15 meters per second. And this is a good range. What if you have a too high velocity or too low? Then you change your initial guess values for the depth and the width of the sand trap. So you may reduce the width if the velocity is too low, or you may increase it if the velocity is too high. And then you converge to a solution where the velocity assumes a satisfactory value. Very good. And then by knowing h and knowing ws, you estimate the time t. And finally, you come to the estimation of the length of the sand trap LD. And then you are done. Your sand trap is designed. Very good. Now, at this stage, let me put on the screen the sketch of the overall barrage. It is coming, just 1 second. Here it is. So this is the sketch of the overall barrage. At this stage, just beware and remember that each of these pools must be equipped with a bottom sluice way in order to allow the cleaning, in order to allow flushing, the flushing out of the sediments, so that you bring the sediments back to the river. This is also important because the sediments, to reduce the human impact, to reduce the impact of this new structure, should be released back to the river. And then you have also to equip this combination of gravel trap plus sand trap with a top discharge, which is something that allows you to give back to the river the water that you may have withdrawn in excess for obvious reasons. You don't need it. So also for preserving the environment, you give it back. But also you want to avoid an overflow of this inside this structure. Because of course, if you get overflows that are not controlled, this is something to absolutely avoid. When you design something that interacts with a river and is meant, like in this case, to take water from the river, you want that the water remains fully under control. You don't want water going out of control. Remember, a natural river is by itself under control because it's in equilibrium. It's under the equilibrium of nature. Nature seeks an equilibrium for the very simple reason that nature wouldn't exist if there was not a natural equilibrium. So if a river exists, it's because the river, it's an equilibrium configuration. Remember that this equilibrium is a dynamic equilibrium, which means that the river is normally under full autonomous self-control. Of course, there might be situations, exceptional situations, where the river goes into an unstable state. Think of an extreme flood. So it may happen that an extreme floods come, which never happened in the past 1,000 years. Okay, this is normal. In nature, this may happen. What happens then? It happens that the equilibrium that has been gained by the river in 1,000 years, suddenly it's shocked and the system goes out of equilibrium. So it may be that new landslides are triggered, that vegetation is scraped away, it's flushed away, etc. And then the system reacts by looking for a new configuration of equilibrium. So nature by itself, it's into a dynamic equilibrium. This equilibrium may change, but it may change, but it's a continuous equilibrium. Okay. Now, if you make a human intervention, you have to, in a way, to conform to that equilibrium. And the equilibrium is such that water is always contained into an environment that is shaped precisely for containing the river flow. So you create an infrastructure that brings water away from the river. You must make sure that this flow is controlled, because in this way it contributes to keeping the equilibrium. So what happens if in your infrastructure water goes out of control? Then it may be that some part of the infrastructure that were not designed for being submerged are submerged. And this is a problem, because it may happen that the infrastructure, after being submerged, doesn't work anymore. So the system goes out of equilibrium. So the concept is, we are working with the natural environment, which is in an equilibrium, which is subjected to changes, but it's a dynamic equilibrium, but still it's an equilibrium, at least in the long term. If we want to make any impact on this natural environment, which is in equilibrium, we have to take care to respect that equilibrium. So if you design a gravel trap and a sand trap for a flow that is 2 cubic meters per second, you have to think what to do if the flow becomes suddenly, for whatever reason, twice that. So the solution is top discharge. There is a top weir, so that in case this happens, like in nature, in case an extreme flood comes, you can predict what's going to happen as a reaction of the infrastructure. And the reaction of the infrastructure is that the excess flow goes in a controlled way over a weir and goes back to the river, which is fine. You have to make scenarios of unexpected situation and make sure that your structure, your infrastructure is still in equilibrium with respect to those situations. It's a dynamic equilibrium, like in nature. So the top weir is not always used. It's used when an unexpected situation comes. So we have to just think at how nature works, and our infrastructure should work in the same way. Okay. Okay, very good. Now, what happens after the system of gravel trap and sand trap? Now we are ready to deliver water downstream, and we may use different ways depending on the water use, depending on the context, the environmental context. In some cases, there is an open channel. There is a channel with free flow. Free flow means that you have water that remains open. A part of your water surface remains at direct contact with the atmosphere. This is open channel flow. So you may have an open channel that brings water downstream. The open channel solution is used when you have downstream your infrastructure mild slopes. Okay, if before using water you have to bring it down in terms of elevation of 200 meters, you cannot use an open channel. Why? The reason why you cannot use an open channel is are manifold. The reasons are manifold. And I want to mention to you just the two most important. If you make an open channel very steep, the water flow is very speedy. You have a high velocity. High velocity means erosion in an open channel, and therefore high expenses of maintenance. High velocity means potentially risky situation. Can you imagine an open channel where water goes at 5 meters per second? It means that if somebody falls into it, then there is no way to get out. Okay. This is one reason. You don't want high speed in an open channel. Second reason, high speed means a lot of friction. Okay, you know that the expense of energy, the energy dissipated by friction, depends in a fluid flow on the square of the velocity. This is something that comes from fluid mechanics. So the higher the velocity, the higher squared the energy that you lose. Okay, you don't want to lose energy. You don't want to lose energy in water. Why? Because you need the energy to distribute the water. If you want to produce hydropower, of course you want to keep the energy because you want to transform the energy in hydropower. If you want to deliver water to people, for instance, in a water supply system, or you want to deliver water to farmers, you need to save the energy of water because in this way you can use it to deliver the water itself. For instance, in an irrigation system, unfortunately, if you have too low energy, then you need to pump it. And pumping means costs. So these two reasons combined together, plus others with lower priority, make the use of open channel flow suitable only when you have mild slopes downstream. So what kind of delivery do you use for bringing water down along very steep slopes, down in terms of elevation of several tens or hundreds of meters? We use pipe flow. Pipe flow is pressure flow. Pipe flow is not exposed, which means that you don't have the risk related to people falling into a channel. Pipe flow is less subjected to erosion than open channel flow. So maintenance is, when you have high velocity, has lower costs. Pipe flow, when you have to bring water down for several meters, allows you to save energy. It's less expensive in terms of energy. It is nice because it's something curious, the fact that pipe flow allows you to save energy when you have a lot of energy, but it is more expensive in terms of energy when the downstream slope is very mild. So if you have indeed a downstream slope that is very mild, it's not convenient to use pipe flow. It's it's cheaper in terms of energy to use the open channel flow. So this is why when your water withdrawal is placed like for instance at the closure of the mountain catchment, so it's placed in a location where the downstream slope is very mild, we use open channel flow. When instead there is a water withdrawal that is placed high in the mountains, we use pipe flow. Let me see if I can show you some pictures of what I mean. I think it is interesting. Let me just open a new window, a Google one. Let me just go to Google. I prefer the Google search engine. And let's see open channel flow. Very good. And let's look at the images. 1 second. I always lose the mouse. I have two screens, which is a good thing, but on the other hand, let me see first the Wikipedia page. I saw a Wikipedia page, and I hope that there are some nice pictures. Okay, this is one nice picture. This is a channel. You see, the channel is running in a very flat area. So in this very flat area, people preferred to use the channel instead of the pipe. Because, as I said, in terms of energy dissipated, energy used for allowing the water to flow, it's cheaper. And of course, there are some drawbacks because, the pipe flow is exposed to, the open channel flow is exposed to evaporation. So you have water losses. Also, open channel flow is exposed to water losses from the bottom of the channel, infiltration. In order to minimize it, we can pave the bottom and the sides of the channel, but this is, from an environmental point of view, is not a nice solution. So there are pros and cons of these two solutions, and but still, open channel flow in the flat areas is often preferred. And it's also cheaper in terms of cost of construction. Let me see if I have some nice pictures to show. I'm just browsing, and look at what I'm doing, because this is something you should do anytime that you have a doubt on what we are talking about. I already mentioned to you, an engineer has to have a full perception of what we are talking about. So when you look at a mathematical relationship, you have always to keep in mind very well what is the connection between the mathematical relationship and the reality. So every time that you study something and you get the feeling that you don't figure out what we are talking about, you should go on the web and look at pictures or videos. This is something that when I graduated was not possible. I mean, now the web is offering an enormous, an incredible opportunity, because it's like making field trips in a very cheap way in terms not only of money, but also in terms of time. So there are many more opportunities. Of course, a field trip is always better than browsing on the web, but a field trip is an opportunity that you cannot benefit from very frequently because it takes one day. So I think the web is indeed a very nice integration. And so I'm also willing to make the search together with you, in order you to see how it works. It's very simple. I mean, you go on the web, on Google, and you see a lot of pictures. And let me just show this one. And here there are a lot of pictures, which I think this is an open channel. Let me expand it. It's a small one. You see, again, it's very flat. It's clear that this is a solution that is used when the slope is not very high. This is a sketch of a pipe, how it works, but this is a pipe that is not under pressure. It's filled only for a part of it. And again, this is used when you don't have much energy to spend. So when you don't have much energy to spend, we want the pipe flow to be partial, not full pipe flow. And this is what happens in the sewer systems. In the sewer systems, you don't want that the pipe goes under pressure. Why? Because if it goes under pressure, then the conveyance of the pipe reduces. Conveyance means capacity to transport water. And this is something that it's usually studied in fluid mechanics. Okay, let's see the other pictures, because I saw that there are other ones. This is another example. I think this is a nice picture. Let's see it. This is a nice picture because this is a barrage, a very small barrage in a river. And it's not a channel, it's a natural river, but I think the picture is nice because this is actually a barrage. The purpose of the barrage, in my feeling, is precisely water withdrawal here. And I cannot say this for sure because I don't see a full picture, a full, I cannot perceive the full structure of it. But my feeling is that this is for water diversion. Okay, so let's close this and let me look at the other pictures. And here you see, if you look on the right, a lot of pictures of open channel. Let's look at this one. And because it's interesting. Why it's interesting? Because here you see that they paved the channel, the bottom and the sides. Why? To reduce infiltration. You see the channel is running in a very permeable soil. This is soil that is dedicated to agriculture, is used for agriculture. It means that the soil must be, of course, prone to infiltration, because when you irrigate, you want water infiltrating into the ground, of course. And you see that to reduce infiltration, they used a canal made by cement concrete, which is not nice to see. On the other hand, it's very productive to reduce the water losses. Keep in mind when we use water for irrigation by using open channel flow, a typical water loss from the point of withdrawal, from the point of delivery, is 50%, and it's including water losses for evaporation, infiltration, and it's quite normal. It's not due to lack of maintenance. It's quite normal that when you have open channel flow, you lose a percentage varying from 35% when they are very efficient. So if they are made with concrete, probably you can reduce to 35% the losses, up to 50% when the network, for whatever reason, is not efficient. And I mean, a water loss of 50% is a lot. And if you work in condition of water scarcity, is something that may be not affordable. And this is very important to keep in mind. This does not mean that we should use pipe flow. I mean, there are several pros and cons with each solution that has to be evaluated. For the open channel flow, one important limitation is the water loss. On the other hand, if you distribute through pipe flow, you still have water losses. Usually they are reduced with respect to open channel flow, but it's very unlikely that a water distribution system reaches an efficiency in terms of water losses of 80%, which means that still 20% of water is lost. Again, this is quite normal, and it is something to be carefully considered. Okay, and again, if you look on the right of the screen, you see several examples of channel flow. All of them, you see that the slope is very reduced. And let me just show you the last one, because I think it's also interesting. It's another example. Yeah, sorry, I couldn't open it, but let's look at it here. But you see in this sequence of pictures, several examples where the channel is paved. Okay, and okay, now let's look at pipe flow, but very quickly. Yeah, I could avoid to close Google. Just 1 second. Okay, pipe flow. And let's look at the image, at the images, of course. Let's see if there is something nice here. And these are all sketches. Okay, interesting to look at this one. If you look on the right, you see a pipe, a very long pipe crossing a flat region. And you may say, okay, in this case, a pipe is used even if the slope is very low. Yes, that's true. And there might be two reasons. And one reason is to limit the losses. And the second reason may be the fact that the pipe is under a very high pressure, because if water comes from high in the mountains, the pipe, after climbing down, then needs to go through maybe a flat area to reach a city, but you want to preserve the energy given by the fact that the water comes from a very high elevation. And to preserve the energy, you have to keep the water under pressure. And of course, under pressure means into a pipe, because in the channel you can't have water under pressure, because a part of the flow is at a direct contact with the atmosphere. So a part of the flow is at atmospheric pressure. Okay, I'm mentioning things that maybe are very trivial for you. If they are, just be patient. I want to make sure that you understand what we are talking about. If they are not trivial, on the other hand, it may be possible. Don't feel like unprepared. It's normal again, and ask questions. So if I'm going too speedy, too quickly, and if you want to discuss more the pros and cons of these two solutions, pipe flow, open channel flow, just let me know, okay? It's absolutely not a problem. And it's also an opportunity to learn, because only if we discuss, we really take advantage of the full opportunity to learn. Okay, very good. I think we can close this parenthesis and go back to our structure. So what happens downstream? This was the question. Downstream, you may have a pipe or a channel. Or it may happen that downstream there is nothing. But let's not consider this easy and the trivial case. Why nothing? Because, for instance, sometimes you are able to use the water immediately without the need of transporting water somewhere else. And this may happen, for instance, if you use water to produce hydropower, then it may be possible to produce the hydropower directly close to the river. And it may be possible, for instance, if you use water for irrigation, that water goes directly to the field. This is quite rare, but may occur. It's infrequent, but may occur. So after withdrawing the water, you release the water through what is called flood irrigation on the field. And so it may happen that downstream there is nothing. But okay, let's say that this is a trivial case. Okay, usually you need to transport the water, so it may happen that you have a channel or a pipe. If you have a pipe and it's a pressured pipe, which means the pipe is full of water, then you don't want a mix of water and air into the pipe, okay? So you don't want into a pipe that is going under pressure, so it's full of water, so the pipe is going to go under pressure. You don't want air, okay? You only want air if the pipe was designed for that purpose. Why? Because if the pipe goes under pressure and there is air into it, this is a big problem. Okay, you may say, why? Please explain to me very quickly. The blackboard, and let me open a new one. Okay, good. Now let me make very briefly this sketch. Okay, suppose that you have a mountain, okay, with a city that needs, sorry, this is very bad. Let me change the color. There is a city downstream that needs water, okay, very trivial scheme. Okay, you need water somewhere here, very good. And to get the water, you decide to make a dam here. And let me color the dam with black. You make a dam here so that you store water here. And then through a pipe, let me draw the pipe in this way, just 1 second. Okay. Very good. Through a pipe, you come down along the slope. It may happen that the pipe goes underground. This is not always happens, but sometimes it may happen. It may happen that the pipe turns back into the surface, and the pipe usually gets to a place where the big pipe is 1 second. The big pipe goes into some small pipes that let me make it in this way. In small pipes that go to the houses. Okay, first of all, you want to keep the energy, because let's suppose that you have a very high skyscraper here. You want water going up to the skyscraper. So you have the water that is going down here and comes to the pipe. And you want the water reaching the top of the skyscraper. So you need pressure, because if the water has no pressure, doesn't reach the top, and you need to put pumps in the basement of the skyscraper. So you want to keep the pressure, and you use a pipe. Very good. Now, this pipe, of course, it's subjected to high pressure, because you have all the water column that comes from the dam. You have this water coming from a very high elevation that presses into the pipe, puts the pipe under pressure. Now, let's suppose that you have into the pipe bubbles, okay? What happens in a pipe, in your experience, when you open a tap in your house and there is air into the pipe, what happens? That everything gets wetted around because water like explodes out of the tap. This is the effect of air into pressured water, okay? Why there is this kind of explosion? Because under pressure, air gets very compressed. Water cannot be very compressed. Water, air, yes, you can compress water and get it into a small volume. And air stays into a small volume because there is the pressure. When you open the tap, the small bubble under high pressure comes out and explodes because there is no more pressure compressing water. Okay, so you have this like, and you get completely wet, drops going everywhere. Okay, this is the effect again of air into water, a kind of explosion. So you don't want this because this is very damaging. Think if there is a kind of tool at the end of the pipe to distribute water, then there is like an hammer head that gives us a great shock to this tool, whatever it is. And even the tap, when you open the tap in this condition, gets shocked because it's like very like an hammer shock that it gets into the tap. So you don't want this. So the moral of the story in technical terms is air into pressured water may give rise to cavitation, what is called cavitation, and may strongly damage the pipe and any other tool that you use for water distribution. So you don't want absolutely air into pressured water. Okay, I hope it's clear. Now let's go back to our figure. What is the way I can make sure that in the pipe that you see on the right, in the bottom right, there is no air. Okay, let me go back now to the blackboard. And let me show you a section, a side view of this top view, a side view of what is called in the figure upstream tank. Okay, very good. Now, the upstream tank, let me change the color. It's something like this. So you have your tank here. And then here you have the sand trap. Here, this is the step. The step is separating the sand trap from the upstream tank. You may place a grid here. The grid is conceived to avoid that you get into the upstream tank floating material. Okay. And then let's depict downstream the pipe. Okay, here you have the pipe. Okay, here we are. Now, what happens to water? Water is coming from the sand trap. Oh, 1 second. Okay. water is coming from the centrap, goes into the upstream tank. And let's suppose that the water level in the upstream tank is here, okay? So here you have some turbulence, water flowing into the upstream tank, and then water goes down along the pipe. So you see that the bottom of the upstream tank is lower down. And why it's lower down? Because I want to keep a submergence over the top of the pipe. So I want to keep a min submergence. If the top of the pipe is submerged, you don't have air entering into it. And what is the value of this submergence? Let's suppose that the flow in the pipe goes with velocity v, okay? So the submergence then should be, let me just use the full word instead of a symbol. Submergence should be greater or equal to, should be at least 1.5 watt, the kinetic energy of the pipe flow, which is V squared divided by 2G. This is a rule of thumb, a recommendation. So keep the submergence at least at 1.5 of the kinetic energy into the pipe. Okay, very good. This is the recommendation, and let's go to the sketch again. And I would say that for the discussion of what is depicted here, what is depicted in this sketch, we are done. And these are the main elements that we have to design. Remember what we discussed in terms of design of the centrap, not the Stokes formula, but design of the centrap, and what we said about the min submergence and why I should make sure that I have a submergence. This is something that I may ask at the exam. A question may be, why do we need to ensure that a min submerged is kept over the top of a pipe flow that is bringing water downstream? And you should say, because I want to avoid that air gets into the pipe, because air into a pipe that is under pressure causes damage, potential damage. And then I could ask you, what is the min submergence that we have to give? And then you should say, okay, it's 1.5 at least of the kinetic energy of the pipe flow. Everything is clear here? Let me have a look at the chat, because it's some time that I didn't look at it. Okay, there is nothing. Okay, good. And okay, let me see how many students are there. Okay, 8. Perfect. Good. Let me just now go back to the page here, not this one. Oh yeah, it was this one actually. Okay, design of river barrages. I'm going down because we are here. Design of the head tank, upstream tank. And you see that there is the rule of thumb, 1.5 squared velocity divided by 2G. Okay, and now let's spend a couple of minutes to talk about the design of the side structures. I am increasing the font, so don't worry. Anytime that I increase, I need to go back to the previous position, because it scrolls the web page. The resizing scrolls the web page. So, okay. Now, side structure, I mean, with side structure, I mean, in this case, particularly the main spillway. When I say side structures here, I don't mean structures that are placed into the sides, but let's say with side structures, I mean structures that are not meant, not directly related to the water withdrawal and water supply. These are structures like the main spillway. The main spillway is not directly related. It's not directly interfering with water withdrawal, but it's still a necessary part of the river barrage. So with side structures, I mean parts of the river barrage that are not directly in contact with the water that is withdrawn. Okay, so what I want to discuss here is the main spillway. And so far, I mentioned that the main spillway, it's has the purpose of allowing the flood flows to go through the barrage without causing particular concerning situations. And so what I said is that for small structures, usually the downstream side of the main spillway is vertical. Okay, and let me refer to again to the graphic blackboard. I think making a drawing is always better, even if I'm not good in drawing. I think I can make an effort and try to use my capacity at my best, and I hope that you are patient with me. So let me just make two examples. There is a first example where the main spillway is something like this. Okay, and let's suppose that here you have the foundation of it, and here you have the riverbed. And here you have the riverbed, okay? Okay, what I said is that in this case, and you have water flowing over here. You have water flowing over here during a flood, and water comes down, and there is here some turbulence, and then water flows down, okay? Okay, what I said is, and of course here you have the current that is, while the current is falling down downstream, you have some void here. This is air. Okay. Now, what I said is that this turbulence is causing erosion, and therefore I place big boulders here, because I don't want this turbulence excavating downstream my structure. Okay, this is what I said. I said that this is for small infrastructures, small barrages. Why this? Because if the river flow becomes very important, then you have a big void. This void here becomes larger. So this part here, where you have air, becomes larger. A lot of air into it. And what happens then? If it becomes larger, there is some friction between the air and the water. And water brings basically air away, and water brings air downstream. It's a kind of suction. And therefore here, instead of having air, here, instead of having air, you may get the void. What happens if you get the void? It happens that the atmospheric pressure here may cause that suddenly you have the water flow collapsing against the wall. Okay, so basically what you get is a huge shock here. A huge shock. Sorry, this is not a color that you can see very well, but I hope you understand what I mean. I mean, it's the water flow that suddenly goes against the side part of the main speedway, and this kind of heating, which may repeat itself several times, may damage the structure. And indeed, our experience suggested that our practical experience suggested that this effect is very relevant. It's something that we need to avoid. So it's not a problem if the water flow has limited size, because, you know, this heating of the water flow, if the water flow is limited, it's not really important. But if the water flow becomes very huge, a huge amount of water, then this heating by a huge amount of water, of course, a large amount of water is more heavy, and the heavier the mass of water, the more shocking is the impact of this large mass of water against the structure. So what was the idea? The idea was to try to solve this problem, and the idea was that, let me make another drawing now. The idea is that if you have, let's start from the riverbed. If you have a riverbed profile that is articulated in this way, and you have a structure here, and let me make the structure similar to the other one with the foundation, and then you have upstream side of the weir that doesn't change, but the downstream side, the idea was to shape it with the same shape that the water flow takes. So the idea was to make something like this. Up to here, and then again here. Okay, so there is this part which is added. Instead of putting boulders to protect erosion, we create a kind of, I don't know how to say in English, but it's a kind of shaped form that accompanies water downstream. So what water does in this case is upstream, it passes through the barrage and then goes down, accompanied by this structure. And there is no separation between the water flow and the accompanying structure. Okay, let me find a very easy word in English that I have not at hand now to term this. Just 1 second, give me 1 second. Okay. I'm looking for, okay, it's a slide. It's like, let me show you just to make some fun a picture, okay? Just for fun. Don't make fun of me. This is what the word I looked for. The word I was looking for in Italian is scivolo, you know, but it's a non-technical term to show you what I mean. Okay, very good. Now, this slide brings water downstream. When the slide ends, you may have still some turbulence. Okay, but it's much more reduced, the turbulence, because water was already accompanied down. The energy was already dissipated, and therefore you don't need a very important protection here, but you can still place some small boulders. Okay. Of course, what is here the engineering question? The engineering question is the shape of the slide. So let me just put it in evidence in red. This shape here. How should this be shaped? Before I look for, before I move forward, let me look for, again, for pictures. 1 second. Very good. I found what I wanted to look for. Okay, you see several figures here, and that basically reproduce what I already sketched. Okay, and also there is one figure that comes from my web page. This is very good. It means that I am getting popular. Okay, so let's have a look at this figure. This is a lab experiment. Just that this allows me to tell you, to mention to you that the shape of this slide was determined also with the lab experiments with the small scale physical models. Okay, and let me see if I can find some meaningful pictures. Because I think, let me see if I can find a picture of the Ridracoli Dam, because I think it is a very nice example. So let me, basically, I anticipate, you see what I looked for, the search term in Google, Krieger profile spillway. Okay, Krieger profile is the name of the shape of this slide. Okay, let me see if I can find first in Italian, because maybe that in Italian, no, there are not more pictures, but let me now find, let me search for Ridracoli Sfioratore, which is the Italian word for spillway. And just 1 second, pictures. I don't think these pictures are not very good. I would need a picture of the bottom, downstream bottom of the Ridracoli Dam, but yeah, I can't find anything very good quickly. Okay, so let me move forward with the description of how this profile was determined. So first of all, what is the name of this profile? We called it Krieger Shimemi profile. It was determined experimentally. It is described by a relationship that I now will show to you. And this is my web page. And you see there is written here an analytical and graphic representation of the two profiles. Why two? Because one is the Krieger profile and the other one is the Shimemi profile. These are two hydraulic engineers. Shimemi was Italian, who independently proposed an analytical relationship for this profile. The two relationships they proposed are empirically determined, and therefore are a little bit different. They are not precisely equivalent, but they are very similar. And so there is a link for the analytical representation. It is in French, but you don't need to read it. And okay, you can also translate, but I don't think it's a good idea. And let me just look at the two analytical relationship. I translated it here. So first of all, you see this figure with the two profiles. And the Krieger one is a little bit more elevated with respect to the Shimemi one. And here they use Shimeni with the final N. I think the correct name was Shimemi with the final M. And okay, and these are the two relationships of the two profiles. You don't need to learn them by memory, absolutely. You see that they are very similar. There is a small difference in the coefficient, 0.47 for Krieger and 0.50 for Shimemi. And there is a small difference in the exponent, 185 and 180, okay? But they are very similar. And you don't need, again, to learn them. I just would like you to know that there is an analytical relationship that can be readily used in order to find this shape of the profile. Here, H1 is the water level upstream. Very good. Upstream over, you see, the water level over the spillway. It's clear that the higher the water level over the spillway, the higher the H1, and the higher should be the slide, the surface of the slide downstream. Good. I think that we can stop this here, and this is just enough for me. And okay, now final, I hope it's final, not sure, consideration. Piping. This structure may subject it to piping. What is piping? I think you already know what is. Piping means that when you accumulate water upstream a structure, this water gives a pressure on the riverbed upstream, of course. You have an accumulation of water, it means pressure over the riverbed. Pressure means energy, means infiltration. Infiltration in the riverbed, because the water, why water infiltrates? Because it is looking for getting downstream in the easier way. So water is a bit disappointed that you beat the barrage. Water doesn't want to wait for accumulation. Water wants to remove the barrage. And what is the reason? The reason is the famous equilibrium we already discussed before. There is a reason why in the river there is not a barrage, because the river doesn't need it. And if you perturbate this equilibrium, then of course nature tries to remove the barrage. So this is normal. And this is what we have to expect without getting disappointed. So water is disappointed because water doesn't like the barrage and tries to find another way to go downstream. And the other ways is through infiltration. So what happens if water succeeds? So water may infiltrate under the barrage and then by flowing in the underground may come out downstream. This is what water tries to do. And if water succeeds, then of course she's very happy and tries to enlarge the small pipes that water found in the underground. And this is through energy. Through energy, water starts bringing some sediments, some dust, some loose material, some soil that is in the underground. Water brings it downstream, therefore enlarging these small pipes that she found in the underground. So enlarge. After a while, it becomes a big flow in the underground, and finally the barrage is ruined. So this is piping. Piping is the bypass of a barrage in the underground, which leads to the collapse of the barrage. So we have to avoid it, very simply. So we have to oblige water to go through the barrage and through the spillways that we have devised for that purpose. So let's look at a sketch that I think it's here. Yes, this is the sketch I wanted to look for. So basically you see here a Krieger profile, but you also see the foundation of the barrage. And water, if wants to go through the barrage by piping, water has to go beneath this foundation. And in order to go beneath it, water has to travel a trip. And the trip is composed by vertical parts and horizontal parts. So let's indicate here in the figure, in the sketch, with LV, the vertical path of water. And let's use the symbol LH to indicate the horizontal path of water. And then we can make the sum of the horizontal paths and the vertical ones. So I can sum LV1 plus LV2 plus LV3 plus LV4. And I can sum LH1 plus LH2 and LH3 to find the total horizontal and vertical water path. Okay, very good. Now, at this stage, I can apply this empirical and let me call it rule of thumb. And it's a formula that is called the Blig formula. Okay, and the Blig formula says that we have to identify a coefficient F, which is given by H. What is H? Let me go back to the sketch. Okay, I go down. H is, it's not indicated here. This is nice. Let me see. Okay, somewhere it's described what is H. H is the upstream water depth over the bottom of the riverbed. Okay, the upstream depth over the riverbed. Okay, H, of course, the higher the H, the higher the risk of piping. Correct? Very good. And now at the denominator, I divide H by the sum of the vertical path plus 1/3 of the horizontal path. And then I get this coefficient. Of course, the higher, the lower the coefficient and the lower the risk. Okay, and so we have reference values for the coefficient F. Okay, and depending, the literature gives these reference values which depend on the types and size of riverbed material. And this, of course, the literature gives higher F values for material that is less prone to piping. And then the material that is very prone to piping has an F value that is lower. Now, this F value again is derived by the literature, and the higher the F, pay attention to me, the higher the F given by the literature, the lower the risk. Okay, this F given by the literature should then be greater than the right-hand side of this inequality. Okay, so it means that if you have a high F, then you can afford higher values of the ratio that is on the right-hand side. Okay, so what we have to do is just to look for H, to compute the vertical and horizontal path of water, and then to compute the ratio at the right-hand side of the inequality. And then I have to get F from the literature and make sure that F from the literature is greater than what I computed in the right-hand side of the inequality. Okay, this is a very, very empirical rule of thumb. It is enough, it is suitable for a first design, for, let's say, for getting an order of magnitude. But if I want to make a refined assessment, I go back to the figure. If I want to make a refined assessment, I have to study the dynamics of the underground water flow beneath the structure. So I have to apply a groundwater model beneath the structure. And this is something that you may have studied in geotechnics. In geotechnics, I think you may have been taught how to apply this simplified groundwater model beneath the structure to get a more refined assessment. If you don't have this background from geotechnics, don't worry. It's just enough for me that you know that this approach is very empirical. And if you want to get more details, there are other more detailed approaches that you are required to use. So what if the Blig lane formula is not satisfied? Then you have to increase the length of the water path. This is the way we can get protected. And the way to increase the length of the water path is, for instance, to increase the depth of the cutoffs. What are the cutoffs? You see that beneath the structure here, there are, look at my mouse, I hope that you can see it. Yeah, you can see it. There is this kind of tooth upstream and smaller tooth downstream. These teeth are called cutoffs in technical terms. And let me show you an example of a cutoff that is being put into place in this figure. These are, I am now expanding. These are cutoffs beneath a structure. You see how they are putting these iron barriers into the ground, and the barriers, you see the iron elements are displaced here. And in this case, they are reinforcing a levee, not the levee is here. I can guess the presence of a levee here in the middle of the picture, and this is an example of a cutoff. Okay, and this with the sheet piles. These iron piles are called sheet piles, and so if we increase the depth of the cutoffs, these teeth, of course, we increase the length of the vertical part of the water path, which is the more effective. It's the more effective to limit the effect of piping. Okay, now we are done. Very good. And it's also 10:44, so I think it's the right time to close this topic. But we have some time for questions, if any. Please, let me share the screen. Good. And please, questions.